Okay, so we have a problem here that I know there's not a lot of writing here. So what this is asking for is it wants us to find the maximum moment at D, and the plus indicates the maximum positive moment at D, due to a couple different cases. First, we have live concentrated load of 4 kips and a live uniform load of 300 pounds per foot. And then we have a dead load system that's 200 pounds per foot. And we talked about in class before about how to handle uniform loads, but I'll show you a different way of handling live ones and dead ones. So we'll talk about that. So the first thing we need to do is generate the influence line for the moment at D. So I'm going to draw a visualization of this. So here's our structure. And remember, at D, I'm going to imagine a hinge. Right? Then let's go back out to my reaction. So with using the Mueller-Breslau principle about the movement of the structure when acted on by the function, in this case our moment, so we're going to assume that, bless you, that we have positive moments in this direction. So how is this structure going to move? We'll start with the point D here. Is it going to move up or down? It's probably going to move up. And then it will then hinge about E to D. It will seesaw over C, and then hinge about B, come up like that. So there's the shape of our influence line. So we can redraw it formally this way. The moment at D and I'll just kind of transfer these points down. So we'll move up and seesaw and then back connect. And also remember that all these dimensions are given. So this is 5, 5, 5, and 10. So I now need to establish one of these values. The two likely candidates to look at would be at B or at D. Which one do you want to look at? Mr. Hudson talked before about looking at hinges, so I'm thinking B might be a good one. Might be the easiest one. So let's think about that. So if I do that, then what I'm looking at is I redraw my structure again, except now I'm putting my unit load, and that corresponds directly to its position right there. Right? So then I have my reactions at A, AY, AX. Now that is actually a hinge. And then I would slide over and I would have BY and
CY.
Yes, CY, thank you. And then EY. So I'm trying to find the moment here due to that load. What I would do is disassemble this structure. Right? So I would have AY, AX. Now that is B, so I would have internally BY and BX. And then of course my unit load is acting right there. Now, remember, I'm trying to find the moment at D, which is way over here. So this stuff's not even on there, is it? So I have to look at its mate, which has BY and BX equal and opposite.
Why do you say that again, Dr. King?
Well, I'm trying to find the moment at D, which is way over here.
Okay.
Maybe I should have put it at D. Well, I've gone this way. I'm going to go ahead and go with it. So that would be CY and EY. Remember, this is 5, 10. Oh, wait. This is 15. This is 5. So there's my load. So what should I do? One or four? 4. What do you see of 4?
I thought the one above it was a 4.
Oh, remember it's a unit load, right?
Yeah.
I'm starting to rethink my selection of doing this here, but I'm going to go with it anyway. So if I sum moments about A, can I find BY? Yeah. In fact, I find that BY times 5 minus 1 times 5, so BY is equal to 1. So I put that back over here. So now I have 1. Eventually, I'm going to cut the structure right here at point D. So when I do that, do you want to work this side or that side? I think the right side. So I want to find EY. So since I now know BY, and I'm looking for EY, what's the best way to solve that? Some moments about C, right? So if I sum moments about C, make sure it's in equilibrium. Okay, about C, I have BY creating positive moment with the moment arm of 5. And I have EY creating... I did that wrong. Did I do that wrong? No. And I have CY creating positive moment with a moment arm of 15. So that means that EY is 1/3. And it's negative. This one's taking a little longer than I anticipated, but that's okay. So now I'll cut the structure there at D. This is 10 feet long. I have EY acting down of 1/3. And then I have the moment. A lot of work to find the moment at D. So what is the moment at D? Well, if I sum moments at the cut, make sure I'm in equilibrium, what do I have? Well, this is a negative moment. And then I have a negative 1/3 times 10 feet. So it looks like the moment at D is negative 10/3. So this value here is negative 10/3.
So even though we just solved for the moment at D, you're still...
Well, this whole plot is the moment at D, but for the position of my moving load.
Okay.
And this is the position of my moving load.
So it's positive 10/3. No.
Yeah, now similar triangles tells you that negative 10/3 is to 5 as what is to 5, so this is positive 10/3. So there's a lot of work. We finally got our influence line. You can see that depending on the problem, the statics might take you a little time to do that. Now that I've done it, I probably would have chosen a position here. Would have been a little easier. It would have still required me to look at both pieces. Okay, so now that I've done that, let me kind of block that off. And let's solve this part of the problem. So with this is my influence line, where should I put my 4 kip live concentrated force to create the maximum positive moment at D? Basically, what's the largest positive value on the curve? Yeah, positive 10/3, which occurs at D. So, in my live load case, I now have 4 kips times 10/3, and that's feet, by the way. I left the unit off. So that gives me a moment of 40/3, and that would be kip feet. And 40/3 is 13.33 kip feet. So there's the contribution to that. Now, what about the live distributed load? Now, the thing about a live distributed load is you get to decide where to start it and where to stop it, because it's live, it's moving around. So where should I start and stop my uniform load to create the maximum positive moment? I should start it and stop it under all the positive areas. So I'm going to start it here at 10 and run it to the end. I wouldn't go over this part because that would create negative.
What if you had 2 positives?
Then you would do all the positive areas. If you wanted the best negative effect, you do all the negative areas.
But all that would total 300?
You would multiply it by it. So let's do that. So that I would have now 300 pounds per foot, and I'm going to multiply by the area of this triangle. So the area of the triangle is 1/2. The base, which is 15 feet, times the height, which is 10/3 feet. So what's all that? I'm going to need some help with that. Let's see, that goes 6, 50, 500. I don't know. Somebody help me with this.
7,500.
7,500. And that would be kip. So it'd be 7.5 kip feet. Right? Because I did it in pounds. This is wrong. This is pounds per foot. Everybody see that? I'll draw a picture in a minute to summarize it. Now dead load is different. Dead load, you don't get any control. Dead load is everywhere. Maybe the beam weighs 200 pounds per foot. It's dead. So you have to get the total area under the curve. So for dead load, it's going to be 200 pounds per foot times the total area. So I'm going to start off by taking my 1/2 out because they're all triangles. And I'll start over here at this side. So the base of that would be 10 feet times the height is minus 10/3 feet. Then this area is going to be 15 feet times positive 10/3 feet.
I have a question.
Yeah.
Since you're finding an area, how do you have a negative subtraction from the area?
Well, this is a negative area because it's negative 10/3.
Right.
And this is positive, so it's positive area.
So aren't you finding the total absolute value?
No.
Oh, okay.
Negative area creates negative moment. Positive area creates positive moment.
Okay.
So what's all that equal to?
1666.7.
So that'd be 1.67.
Correct, yes.
1.67 kip feet. And we just have to add all that together. I don't know what that would be. So the total, so now the moment at D max would be the sum of these three. What's the sum?
22.5, roughly.
So that's the maximum moment at D created by that. Now, what would that look like? So let's redraw the beam. So we have a pin, a roller, and a roller. First of all, the dead load went over the entire structure, right? So there's the dead load. I'll just say DL. The live load went where? Just over this section, which would be right about here. There's the live load. And then where'd the concentrated load go? At D, which is right about here. So that's the loading scenario that created this. So that was the 4 kip force. The live load was 300 pounds per foot. And the dead load was 200 pounds per foot. So remember, dead load goes across the whole structure. The live load you can position to create the maximum effect. So this is a good problem because not only does it show you how to draw an influence line using Mueller-Breslau and then your tools, then we apply it with some actual loadings and are able to predict the maximum moment and also show the loading configuration. So any questions about that? I think we'll probably work some more. So if you didn't get it, we'll work some more. Just acting up and recording this as I'm talking.